revolution of economics, politics, and government. Welcome to the blockchain.
Our next speaker, he's a software architect at VirtusaPolaris. I'd like to invite Mr. Omega Silva to speak on blockchain under the hood.
Good evening, guys. Hi. Before I start, can I get a show of hands just to understand how many of you guys are from a technical background and who are not? Super. All right. All right. So at a very high level, just to explain the concept and what things are. So we have two people, one owns an asset and that person wants to transfer this asset to the other person. Now, if you do it in a digital framework, the other speakers spoke about this as well. We need to keep track of it, right? Now, somehow assume that we create these transactions and we now have a set of transactions that's out there. Now, we need to somehow prove that some person, in this example, Bob, transferred a particular asset. Could be money, it could be a land title, it could be diamond, anything, to the other person. Now, the trust issue that's solved by these central bodies like banks comes into play. Now, we have a set of transactions, but now you need to somehow prove that the transaction happened. Now, this particular model works on a peer-to-peer network, and what this peer-to-peer network basically does is it groups these transactions into blocks and it orders them. So this ordering basically does two things. It basically tells you when transactions actually happen. Now that's quite important to understand or rather to solve the double spending problem. And there are ways of proving that this particular transaction happened from this particular person to the other person. Now at a very high level, this is basically the overview. Now before continuing into blockchains, let's have a look at how these transactions are represented in this particular way of dealing things. Now you have names for the two people who are involved, but in this particular framework, you get public and private key pairs. Now, each person who actually plays in this particular domain have a public key and a private key. Now, when you do a transaction, there are few components of these transactions. Now, a transaction should always have inputs. I'll explain what these inputs are, and it should have outputs. Output is basically saying, okay, who, or rather in this particular transaction, how much of asset is sent to from the person A to person B, and there could be many people who the assets are getting dispatched from a particular transaction. Now the interesting thing is this. Now Jamin talked about the traceability factor. You don't have a particular value within a transaction. That is to say, if I am actually, if I want to transfer some amount of assets, let's take the currency example because it's quite easy to explain. If I want to transfer some bitcoins or some money, I don't have a single figure saying I own this much of money within me. It's basically proven. So from the very first transaction, which gives me some assets, let it be money, how that money is transferred from one person to the other, that's maintained linked. So each of these inputs is basically proof to figure out how I got this amount of assets. So if I'm saying, okay, I'm going to transfer, in this particular example, I'm going to transfer 7 units to another person, I need to prove how I got these 7 units. So it relates to certain other transactions and they relate to certain other transactions, and it goes on until up to the very first transaction that was ever created. So when you're actually dealing with this, you need to first figure out, okay, this is the transaction chain, and therefore what are the amounts that we hold, right? And the other interesting thing is this. Now assume that you right now have 7 units and you only want to transfer 6 to a particular person, in this particular case Jack. Now there's 1 left, so it has to be balanced out. So the remainder has to be transferred back to yourself, right? That itself is a transaction, right? So that's basically how these transactions are kind of linked. So that you could, from the point, from the inception up to the current point, you could prove how the assets got transferred and how they were used. Now, how do you prove that the transaction is valid? So, what basically happens is, when you create this particular transaction, now I said people have public keys, and if just show of hands, people who understand public and private keys? Fantastic, super. So, at a very high level, what it basically does is, these are more like passwords, right? I have a public password and a private password. How it works is, this is a mathematical scenario. So, I encrypt something with my private password, that's only known by me, and the public password is known by everyone. So, if I encrypt, let's say, a letter using my private password, I send it to someone like you, some of my friends, let's say, and they know my public password. If it's correctly encrypted by my private password, they can decrypt it and get what's encrypted out there. So, what basically happens is, the sender encrypts the entire transaction, all this content, with its private key and sends it to Jack. Now, Jack understands what Bob's public key is, public password is, and he could basically decrypt the signature to verify whether it actually came from Bob. So, that's how a transaction verification happens. So, that in this particular way, you could prove that the particular transaction actually, or rather a particular amount of asset actually came from the person that it claims to be. Right. Now, the double spending. So, these transactions traverse through a peer-to-peer network. Now, the interesting thing is this: when these transactions happen, when I create a transaction, it gets populated to the peers that I'm connected to, from those guys to the peers that they are connected to. But the order of the transaction cannot be guaranteed. Now, in this particular case, let's assume the transaction that we earlier saw, this goes to Jack's computer and it goes to Alice's computer, Tom's computer likewise. But if Bob is a malicious user who wants to hack the system, he could basically do something like this. Now, he sends some amount of money to Jack and waits until Jack ships some goods, or accepts that he received money or whatever, and Bob creates the same amount of transaction. So, the same amount of money or whatever sent to Jack, you send it back to Tom, saying, hey, you also have this amount of money that I'm sending to you. Now, the interesting thing is this: in some cases, this particular transaction might reach Alice's computer before transaction 1 reaches Alice's computer, right? Now, when that happens, now I told you there's a series of transactions linked to each other, right? Alice's computer will validate whether the so-called transaction has been used earlier, right? Now, at this particular case, Alice doesn't know that T1 happened, she only knows T2 happened, right? When T1 hits Alice's computer, she will say, hey, hold on, this cannot be right. Now, T1, I've received that Bob has spent like 6 bitcoins or currency or whatever already. Now, you are saying me, you are telling me the same set of transactions are being used in this particular transaction. So, T1 refers to the same set of earlier transactions which T2 refers to, and Alice would say, hey, I have detected an anomaly. Now, T1 is valid, rather T2 is valid, T1 is not valid, right? So, that's how, if you want to play carefully, a double spend attack would happen in this particular network. Now, how do we solve this double spending problem is the key. Right. Now, so the double spending is basically solved by collaboratively agreeing on the order of the transactions. Now, I earlier talked about order of the transaction matters. In this particular example, the previous example, if the order was agreed within the network, then the double spending could have been prevented, right? Now, what happens is this: now you have this set of transactions and any node. Now, why I use any node here is, when a transaction happens, the transactions get propagated through the peer-to-peer network, right? So, at a given point, any node would have all these transactions which are not put into blocks. Now, any node can group the available transactions and put into a block, right? But no one has agreed that the block has been created. Now, how do we agree that the block has been created? That agreement happens through solving a complex mathematical problem. So, this particular problem is of this particular sort. So, what you do is, now you create a block with n number of transactions, and you have that particular content plus a random number, right? And you use a function, let's say hash function, right? And you always check whether this hash function, the output that it generates, is lesser than a particular amount of value, right? Now, if you hit this particular condition, this particular node says, hey, I've solved this. This is the signature of this particular block, and communicates it to the entire set of peers that's in the network. Now, this is not easy, right? For a typical computer to solve this particular problem, it would take years. But since we are doing it in a peer-to-peer network with so many number of nodes, the chances of one node solving it, because this is a randomization, right? One node solving this can be brought down into a manageable amount of time. Right now in the Bitcoin network, as Jamin said, it's 10 minutes, right? So it depends. This basically this time that it takes to solve this particular problem is a function of the computing power that's available, right? Now you basically figure out. So it's basically saying, imagine you write a for loop, right? I mean you repeat every iteration, you guess a number, and apply that to this particular formula and see whether it's below a particular value. If so, fine, block is solved, right? Now, once the block is solved, you communicate that to the network, and everyone accepts, hey, we have a properly agreed block that could be attached to my blockchain, right? Now, it might not actually represent the right chronological order of the transactions that were created. It would not, it might not. But this is the common agreement, right? As long as the majority agrees, right, no one can hack the system saying one transaction got created before another, right? Cool. Now, so this particular process is called mining. Now, this term was coined by blockchain, I believe. So right now, the people who actually connect to the blockchain network are given some incentive. So they are getting bitcoins for doing this, right? Now, yeah, we have mostly covered this. Yeah, cool. Right. So let's talk about blockchain. Now, a block that's solved would have these three particular components. Now, it will have a block ID. Now, this is the answer to that mathematical problem that was solved earlier, right? It becomes the block's identifier, right? And it will have a set of transactions, and it will always point to the previous block, right? Same goes like that. Now, to get this hashing function, right, you could use something like SHA-256, and why we go with a proof is basically, if we go with something like a timestamp, just to get the order of the transactions, the timestamp could be easily spoofed, right? You know how to spoof the timestamp, right? And what happens is, now I told you earlier, solving this mathematical problem, it entirely depends on how much of computing power that you have, right? Now, the more computing power that you have, the time that it takes to solve the equation becomes lesser. So time to time you need to recalibrate the system to increase the complexity of this mathematical function, right? Otherwise, the amount of risk or the vulnerability of the system will increase. Right. Now, it's quite rare that two blocks are solved and confirmed at the same time, but it could happen. If that happens, right, what happens is, now a block gets solved and it's communicated. Now, if two blocks are solved, there could be branches like this, right? So node 1 can be having like block 3 and 4 which are solved, and block node 2 might be having block 3 and 5. Now we need to do some tie breaking. So what basically happens is, the correct branch is decided by the next block that gets solved, right? Now, if block 6 gets solved and that particular block reaches node 1, what it basically does is it attaches that to the first block that it received. Now, assuming that block 3 was the first block that it received, it attaches B6 to B3. And then what it does is it drops the other branch. Now, this is quite interesting. This is a solved block. But when you have the largest branch, the longest branch rather, the other branch automatically drops, which means the transactions which were grouped to this particular block again goes into free space. They have to be again brought back into a block, solved and confirmed, right? That's why I said there could be transactions which were created earlier but added to the blockchain later because of this particular phenomenon. And if you have to hack the system, the only way that you could hack the system is by creating the longest branch. There is no other way of hacking the system, right? So, this is the confirmed blockchain after this, right? So, B6 is confirmed and it gets propagated to all the nodes saying, okay, I have confirmed B6 comes after B3 and everyone agrees. And B5 and B4, they get lost in the system. Right. So, before continuing with the hacking part, right, I just want to touch upon one of the hashing algorithms that we have here, right. Now, SHA-256, this is what's used in blockchain, Bitcoin I believe. So, see this particular input, this is the hash. So, hash is basically you get some content and using mathematical functions, you create a unique identifier to represent that content, right. This is a one-way thing. So, you cannot use this particular identifier and recreate this particular text, right. Now, the addition of a single period changes the hash entirely, right. So, a small amount of change in the content, right, introduces a very huge variance in that identifier, right. Keep that in mind. Now, if you have to hack it, right, now assume now this block 2 is solved. Now, I am a malicious user, I need to alter something and I need to push that block into the blockchain and confirm it. Now, if you could remember that earlier slide, I said that every block refers to the previous block, right. Oops. Right. So, which means if I hack this particular block, if I want to replace this particular block, right, all these blocks are no longer point to this particular block. That is because any alteration in this particular context changes the ID, right. So, if I am to hack it, I need to decide a particular block which I need to hack, and from that point onwards I need to replace all the other blocks, right. So, that is why we say that this is very hard to hack. The only way that you could hack it is getting the majority of the computational power, right. So, by getting like more than 50% of the computational power, you have 50% chance of creating 2 consecutive blocks, right. But yeah, now this has been proven up to a certain extent. Now, in the Bitcoin network, what they have realized is rather than joining as individual nodes, they have grouped and created one distributed computational unit, and people join this because it's quite easier to solve the blocks quickly, and they get a guaranteed income. Now, there's a particular group, I can't remember the name, they have identified that they have solved 6 blocks consecutively because they were having that amount of computational power. So, what they have done is after detecting that, they have voluntarily reduced the amount of computational power that they have had, right. So, right. Now, the other interesting thing is this smart contract concept. Now, this is a software, right? So, in a transaction, depending on the implementation, it could be in certain other ways. You could introduce code, right? So, for example, if a transaction gets to a particular place, you could execute some piece of code. Now, this could be used to, let's say, execute a contract based on time. Let's say you, give some incentive to a miner, right? Saying that, okay, thank you for, solving these blocks. Here's something for you, right? All this could be programmed, right? Now, depending on implementations, Ethereum, Hyper, depending on certain fabrics, how this implementation is created, it becomes different. But this is a pretty cool concept to have, where you could actually program or introduce a script that you could, define, enormous amount of things and introduce that to a particular blockchain and a transaction. Okay, concluding, it's basically a distributed database, as Conrad, introduced earlier, running on a peer-to-peer network. The order of the blocks is not determined by chronological order, but it's proven by a mathematical solution. The authenticity is proven by cryptographic techniques, as we discussed, and the transactions could be actually, programmed, right? So that's what blockchain is. Hope you understood how this runs under the hoods. Cool. Thanks a lot.
Thank you, Mr. Silva.